This video is about real power. It corresponds to section 35.1 of the Applied Analog Electronics textbook. We're going to look at this real power in two different ways. The first way is to look at it entirely with real valued functions. So we'll have, say, voltage is cosine or A times cosine of omega t plus phi, and I is B times cosine, same frequency, omega t, but with a different phase. Let's use a C here instead. Okay, what does that mean? Power is just voltage times current, if we're looking at real valued things. And that's going to be AB cosine of omega t plus phi and cosine of omega t plus c. And here we get to the part that I hate, trigonometry. Cosine times cosine is just a mess. If we want to take the average of the power, we have to integrate that thing. So we need to use a trigonometric identity to try and simplify the integration. And I don't really remember trig identities. I have to look them up every time. But the one that I use here is cosine A times cosine of B is 1/2 of cosine of A plus B plus cosine of A minus B. All right. Using that trig identity with these values of cosine, we will get power equals 0.5 times AB times, well, the sum of them is going to be cosine of 2 omega t plus phi plus c plus cosine of phi minus c, where the omega t's cancel when you do subtraction. Now you might think, God, that looks even worse than before. But when we're integrating, things get simpler, because this part here with the 2 omega t in it, that's a periodic function. It goes up and down symmetrically around 0, twice the frequency of the voltage or the current. When we integrate that, it's 0. So that now gives us a simplification that the power is just 0.5 AB times the cosine of the difference in phase. If they're in phase with each other, this cosine is 1. The difference here is 0, cosine of 0 is 1, and we just get 0.5 AB, which is the power that we got before when we looked at an AC signal, say, going through a resistor where the voltages and currents were in phase. If you've got things that are 180 degrees out of phase, so the voltage goes up, the current goes down at the same time, well, what that means is you're not dissipating any power in that circuit, you're taking power out of the circuit, and so you end up with a negative power dissipation. And then there's the other sort of special case where phi minus c is the 90 degrees out of phase, and that gives you a cosine of 0. And so there's no power dissipated. When do you get 90 degrees out of phase? Well, if you've got the voltage and the current going through a purely reactive component, like an inductor or a capacitor, then you end up with a 90 degree or minus 90 degree difference in phase between the current and the voltage, and there is no power dissipated in such a thing. So this is the real power done entirely with real cosines. But I told you I hated trigonometry. Turns out there's an easier way to do this analysis, particularly when you start looking at messy impedances and stuff. And that is to use something called RMS Phasers. And these phasers were named before the Star Trek weapons. So, I mean, this is where they got the name from. The RMS phaser for let's say we had, as before, voltage is A cosine omega t plus phi. The RMS phasor for that is A over square root of 2 times e to the j phi. And what we do with this is we can now look at this thing as a multiplier. So the phasor gets multiplied by e to the j omega t. So this is in some sense the amplitude. This is the amplitude here and phase, and this captures both the amplitude and the phase. But we've got that over square root 2, so that makes this thing an RMS phasor. So this is the RMS voltage of this waveform over here. And that's an important trick. If you can also work with amplitude phasors, where you would just put an A instead of an A over square root 2, but then you have to keep keeping track of where do the voltages change, where do you get that half that came out of the previous trigonometric thing. If you deal with RMS phasors, so you just say, what's the RMS voltage of the signal? What's its phase? You can write it as an RMS phasor, and then our calculation becomes very easy, because what power is V times I star, where both of these, we have RMS phasors for both of these. I star, I should explain that notation, that's the complex conjugate. And the complex conjugate of something like, say, x plus jy, take the complex conjugate of that and you get x minus jy. All you've done is negate the imaginary part. And we can also look at it in sort of polar notation. If we take some amplitude times e to the j theta, or let's do like RMS phasors. The complex conjugate of that is just a over square root 2 still, e to the minus j times the phase. So negating the phase is the same thing as negating the imaginary part. Okay, with this notion of complex conjugate, with RMS phasors, if we write down the power, the average power is just the phasor for V times the phasor for I complement, which is to say it's AB over 2 e to the j phi minus c, using the same sort of notation we had before. And again, we've got the same notion here that there's an AB over 2, which is sort of the overall average power, and a term that depends on the phase between them. But notice that this term here always has magnitude 1. This is just e to the j something that's always going to be on the unit circle. What's different is that it's got a real part and an imaginary part. We can write that here as cosine of phi minus c, plus j times sine phi minus c. And the cosine part here should look familiar from the previous page when we were doing this stuff all with trigonometry. That's the real part of the power. Notice that this power here is a complex number. The real part of it is the same thing as we calculated before using trigonometry. That is the real power. So the real power is the real part of the power. Obvious name. There are two other concepts that we have here, and those are, maybe I should start on a sheet of paper. So, real part of P is real power. if we look at the imaginary part of P, that's called the reactive power. And there's another thing, if we look at the magnitude of P, that's called the apparent power. Now, when we're looking at a real system where we've got the voltage across some device and the current through the device, so we're looking at the impedance of the device, the real power is the power that's actually dissipated in the device. If you take a look at a resistor, it's all real value. The power is all real power. And the reactive power is 0 then, and the apparent power is the same as the real power if we just got a pure resistor. But if we've got something like an inductor or a capacitor, then all the power is reactive, which means we're not actually dissipating it. It's being stored in the system, and it sort of sloshes back and forth between components in the system without ever going away. The real power gets dissipated, usually as heat. Apparent power is what you would get if you just say, take the two RMS powers, the RMS voltage and the RMS current, multiply them together. That's the apparent power. And that's sometimes useful to compute, but most of the time we're going to be interested in real power, the stuff that actually gets dissipated. Now there are some engineers who like to use different units for these different sorts of power. Technically, if you want to be very, very careful, you should use the different ones. This one, because this is the one we really care about, that's in watts. The reactive power, let's see if I can remember what that one is. That one is done in VARs. And the apparent power is done in volt amps, because we get it just by multiplying the RMS voltage times the RMS current and ignoring the difference in phase. For this class, we're not going to be this fussy. You can use the term watts for everything. And the assumption is that when you use that term, you're talking about real power, unless you explicitly say reactive power or apparent power. So if you want to talk about one of the other things, if you want to talk about apparent power, you've got to say so. You can't just say, oh, this is P. I should actually say, if you just use P by itself, without real part or imaginary part or magnitude, that's complex power. And it's the easiest thing to compute. You know, it's just VI star. And most of the time when we compute complex power, if we want to plot it or do something else with it, most of the time we're going to be wanting to report the real power. And so we're going to need to take the real part of this. That's different from what we were doing, remember, with impedance. Because when we looked at impedance, we were usually interested in the magnitude of the impedance. For power, we're usually interested in the real part of the power. Okay. I think that's probably about it for what we have here. I guess there's one more little thing. If we've got an impedance, V equals I times Z, we can go through and say, well, the power is I times I star times Z. One nice little trick that you should be aware of is that I times I star here is the same thing as magnitude of I squared. You can see that very easily if you just look at it in terms of x plus jy times x minus jy. Multiply that thing out and you get x squared plus y squared. The plus jy and the xy and the minus jxy cancel. So power is magnitude of I squared times Z, where again this I is the phasor, the RMS phasor. So if we take a look at the RMS current, square it, so we end up with a mean square current times Z, that'll give us that'll give us the power here. And notice that this is a real number. The phase of I doesn't matter here. Z is not necessarily real. So the fact that the real power, reactive power, and apparent power all pretty much depend on what Z is as a complex number. We can do the same thing if we want to do it in terms of voltage, where we can write I equals V over Z and get power equals V times V star over Z star. And that gives us magnitude of V squared over Z star. A little bit messier than it is for current. But the notion here, if you take a look at what happens with resistors, where the Z is just R and Z star is just R, these are exactly the same formulas as we had for the power for DC and resistors. But now, remember, this is not amplitude we're dealing with, but RMS voltage and RMS current. So when we do the phasors, it's the RMS value times e to the j phase. Okay, and I guess that's probably enough for today for real power.